So mathematical models are formed from equations, and there is a kind of a set of steps that's very useful to follow when you are first encountering a new model or are constructing one of your own. And in this example, I'm going to use the idea of some kind of population versus time. So let's say, imagine I have a simple model. This is population versus time is 1,000 times t plus 200. Okay. So this is the equation, and there are a number of things that we want to pay attention to with an equation like this one. Step one, we want to look at the units of all the different things that we're looking at. We want to look at boundary values. Okay. We want to look at limits. And we want to look at any kind of unusual values. And I'll walk you through kind of this in this particular case. So let's start with units. So first thing, so if this is population, this is going to be some kind of number, like a number of individuals. Sometimes it might be population density, and it might have something a little bit different. But let's just say it's a number of individuals. And the variable t is going to be some kind of time. Now, depending on the process you're looking at, you may have time in seconds or years. Let's say, for instance, this is in days. I'm going to put the units in brackets just to be clear. This number then is the slope. So this could be kind of like a y equals mx plus b. So y equals mx plus b. In this case, the x is time, and so the slope is 1,000, and we can ask what units it would have to have. And the thing is, it would have to have units such that it would cancel off days and give you the number of individuals. So it has to be some kind of number per time, except number per days. The other term, the b term, okay, the intercept, has to then have the same units as the population. So this has to have the same units as the number. And so this gives you a sense for what these numbers would actually mean. So this has to be some kind of population, this 200. This has to be some kind of rate, some population per time per day. So it gives you some intuition. When I talk about boundaries, so that's the kind of units. When we talk about boundaries, what we're talking about are things like what happens to the equation when the time t is equal to 0. Okay, in this, usually it's boundaries refer to places where the equation takes on a simpler form. So time t equals 0 means population is equal to 0 plus 200, or is equal to 200. And so this is what it does then is it tells you the meaning of some of the constants. So this constant here is simply the initial population. Okay, so that's what that would be. So it kind of gives you a kind of an intuition for those things. The boundary condition might look a little bit different. You could have an equation that looks like this: p equals, say, 1,000 times t minus 5 plus 5,200. Okay, these are in fact equivalent equations. You can see that if you just kind of multiplied out the 1,000 times the t and the 1,000 times the -5, and you'll get the same equation. Here the boundary really is time t equals 5, and at that time the population is 5,200. And so this is no longer an initial population, but it's the population at time t equals 5, and so it might be the place where you actually have data. So in that way, you have these this would be kind of a boundary. Now, limits are things like what happens when t gets really big, say goes to infinity. Clearly, what happens here is we end up with population getting to infinity. What happens when t is say negative infinity, go back in time, population is negative infinity. Now that's one of the unusual values. So essentially, there are values for t such that the population goes negative, and that doesn't make any physical sense. And what that tells you is one of the kind of limitations of the modeling process. All models are wrong to some extent. They're all approximations, and they break at a certain point. So if you can find areas where the variable gives you clearly ridiculous results, then we cannot trust the model in those regions. And so we had to kind of see where is this model actually valid. Another unusual value, for instance, imagine what happens if time, t is equal to, let's say, 0.00001. All right, that means the population becomes 200.1, and we have this kind of odd, tenth of an individual there, and so that's an unusual value. And so again, the model is an approximation. Maybe p is not really number, maybe it's measured in billions, in which case a tenth of that would be tenths of billions or 100 millions. Or maybe it's some kind of population density, population per square mile, in which case 0.1 would actually mean that you would have 0.1 person per square mile, but some square miles you wouldn't have anyone, so you might just have in 10 square miles about an average of one person. So it tells you some of the kind of limitations of the model itself. In the next video, I'll do the same process, but for a different population model, and kind of walk through some of the same ideas.